Okay, so just the summary of what just happened there in 7.2 is that the volume is either going to be pi times the integral of the big R, big radius in terms of x, minus the little radius dx, or if it's turned side to side, that'll be pi a, sorry, not a, c to d, the big radius in terms of y squared minus the big radius, the little, too much talking, little radius in terms of y. So big R minus little r. And again, this will be kind of thinking like if the revolution is around an axis like this, and you're thinking up and down on your little things that you're spinning, it's either this to get a disk, or it'll be something with a hole in it to get this. So it's kind of like if it looks like a perpendicular already, like if your strip is perpendicular to the axis of revolution, it'll look like this. Same thing the other, if you do the y-axis or any sort of vertical axis, then you're going to want to look left and right. So if your thinking is perpendicular to the axis, so if you're acting perpendicular to the revolution axis, then you end up getting the disk or slash washer if you have a hole method. So that's what 7.2 is. And oftentimes, the worst you could do is reverse these and get the negative of the answer and go, oh yeah, that was wrong. I did the wrong R's. When you start moving the axis around to different places, it can get a little tricky, but I'll let you work on some of those and we can chat later. 7.3, we can go into more theory on Monday, but maybe just for today, it's going to be now, instead if we're acting perpendicular to the revolution, if we act parallel to the revolution. So it's going to be the exact same volume. So they are volumes. We are just thinking about it in a different way. So what this means is if we have our axis and we're revolving this way, then let me put x in here. And if we're thinking up and down for our functions, but we want to revolve it around a vertical one, then we don't just get radiuses because we don't just get disks. If we were to take this object and spin it around, it would look like a really tall thing spun around. And this is no longer like I mean, it's probably technically a really thin washer, but it looks more like an air filter. Like if you ever change your air filter in a car or in a lawnmower or something like that, it's like these circle things that you drop in. So they're really skinny on the filter part, but then they have a pretty big wide radius. So as opposed to being a disc or a washer, this thing is called a shell. And the volume of the shell is going to be different. That volume is going to be more like taking the circumference of a circle and lifting it up a certain height. So it's going to be like circumference, which is going to be 2 pi times the radius. So as opposed to pi r squared h, now we have 2 pi r h. And since both of those are linear units, we get a unit and another unit. So we're sort of missing that third unit to get a units cubed. That'll come from a little delta x, which is like the width of these individual things. So we have a radius and we have a height function that we have to deal with. And in the picture, it's probably new. We start with this picture. The radius is still kind of where we expect it to be. The height is right where we expect it to be. And again, it's not the full cylinder. It's like the really thin rim, like of a can. So you can't really treat it as like a washer anymore. It's a very thin, what's called shell. But if we translate this back, now we get a radius function this way, which really, in this, this is often just going to be x. And then we have a height function here, which is going to be governed. It's going to be governed by your functions. And so you'll have an equation that looks like this. And so when we get to the actual total volume formula, to make it look like the one up at the top, this will be 2 pi the integral from what this is a to b for x. So then you'll have a radius function, and you'll have a height function. So, whereas before the hard part was how do you find the big R and the little r? Well, now it's how do you find this like little r here, and how do you figure out what this height function is? So if you know the formula, you know which one you're doing, then you just have to figure out what those two things are. And again, oftentimes this little radius function here is just going to be x, because that's the distance that you've traveled from the y-axis. You get over to a point, it's just, well, it's whatever the x-axis is. It doesn't even care what the functions are. They only care what the functions are up and down. So, too much formulas already, but we'll try an example. So, for example, let's take y equals 1 over 1 plus x squared, and go from x equals 0 to 1, and revolve it around the y. Okay, so picture time. Let's draw the pictures. So we draw this graph. We plug in 0. We get the point 1 over 1, so that's 1. We plug in 0 or 1, we get 1 over, we get a half. So those are the beginning and ending points. If you draw the rest of the points in, it kind of looks roughly, roughly looks like that. And so you're going to want to take this object and you're going to want to spin it now around the y-axis. And if you do that, you just get something. Let's see, this comes down, 1. You revolve it around, you kind of mirror image on the other side, and then everything becomes circles. So I don't know, this top kind of looks like a circus tent, and then it's like everything below the circus tent, and you get that volume there. Now, the problem is if you were in the previous one, you revolve around this, you'd want your thinking to be perpendicular, so you'd like to think left and right. And just like in section 7.1, if you think left to right, then you'll have a right function and a left function. The problem is you have a right function until you get down to a half, but then below that, it changes. So if you could do this by the disk method, and after a while, we're going to just say, pick your method or do it by as many methods as you can think of. You'd have to at least break it up into 2 pieces, because the left-right thinking at the top is different from the left-right thinking at the bottom. So instead of thinking right-left, we want to think up-down, because we only have one top function and we only have one bottom function. That makes things a little bit nicer. And if we do that, parallel, this thinking here up-down is parallel to our up-down axis that we're revolving it around. So parallel means that we want to use the shell formula. And so that volume will be 2 pi times the rate times the integral. These things are still going from like 0 to 1. I just have to figure out my 2 radius function and my height function. So we come back to our picture. Well, the radius is going to be sort of here. And my height is going to be here. So when you revolve this thing around to make it again into a shell here, the radius is inside and the height is up and down. So you transfer that back to the picture, the radius and the height go back to there. So the radius function is as well, however far out I am. It has no idea what this function is, so it's only thinking left to right, how far over I am. That turns out to be, well, whatever the x coordinate is exactly what my radius is going to be. If I'm like half a unit out, then the radius is a half. How do I figure out this height function? Well, the height is exactly the same thing as like the y coordinate, because I'm coming all the way down here to the bottom. So that's exactly the y coordinate. So that means to figure out that y coordinate, I use y. But to get the y coordinate, it's the same as finding the h. So the h is exactly my height function, which is the function itself. So trying to figure out what these little r and these little h's are in this case, you just have to look at the picture. Voice is definitely going here. And that's the setup. Now, when you get to the end, the rest is now Chapter 6 methods. Figure out how do you do this integral. Let's see. So 2 pi, 0 to 1. I would write this as x over 1 plus x squared. Come over here on the side. That would be u equals 1 plus x squared. du is 2 dx. So that's my u sub. I would get 1/2 the integral of 1 over u, so that's 1/2 natural log. So then when I would come back over here and replace, I'll get the natural log of 1 plus x squared, technically absolute value, and then 1/2 of that. And then I plug in my bounds, 0 and 1. So if I do that, I'll get the half and the 2 will cancel. Pi times the natural log of 2 minus pi times the natural log of 1. I'm plugging in 1 and 0. And that second part there is just 0. So I get, look at that. I'm now mixing them. Pi and natural log in the same answer. No. Again, it's just a simple, nice polynomial, and the answer ended up having pi's and logs in it. Ah, that's not fair. That's not cool. So that's probably, we'll come back and do more, so we'll sort of push 7.3 homework back a little bit. And the last sort of 20 minutes and see if you got questions on homework here. Either previous, new homework, old homework, concepts you're still like, I don't get it. Go for it. What do you got? Some areas, maybe some L'Hopital, maybe some improper integrals. Those are the recent things anyway.
Could you do 23 from the homework last night? So that was 7.1.
Okay. Yeah, this is a pretty good one to put it all together. Okay, so what it says is we'll just do y equals x squared and y equals x plus 2. So we want to find the area in there. So this point here is 2. The intersection here is -1. The intersection occurs over here at 2. And boom, we just want to find the area. Now, if I just said find the area, you probably will just go, well, all right, so I take the area is the integral from -1 to 2. I take the top curve, which is the line. I take the bottom curve, which is the parabola, and you work that out. And that is part A. Part A. Did you get that for part A?
Yes, I did.
Okay, so that's part A. Now it's being mean or maybe trying to, I don't know, it's good practice, but excuse me, about to sneeze. If you think up, down, that works because the top curve is always the line and the bottom curve is always the parabola, no matter where you are in there. The problem is if you think left, right, you're going to run into a problem because the right curve is kind of like from here up. That is the right curve. That's definitely the right curve. But the left curve will depend whether you are above that dotted line. This will be the left curve. We call that like left curve 1. If you're below the line, then this is like left curve 2. So at least you're going to have to break it in half, depending on what those bounds are. So the first thing to do is to figure out, where is that dotted line break? And you can see that that's going to occur over here at -1. Next is -1. This is at height 1. And then over here on this far side, how far do you go up? The answer is, well, that's going to be when you get all the way out here at this corner. That's when x is 2, you're at 4. So on the y-axis, I just sort of overlay it off to the side. This is at 0. This is at height 1, where that dotted line is occurring. And this is at height 4. You're going to have to break it into an integral, a few things up and down this way, and you're going to have to break it into an integral that way. So one of the integrals will be from 0 to 1, and the other integral will be from 1 to 4. And those will be the y. And now I'm thinking side to side like that. So I'm going to need from 0 to 1, I'm going to need the right curve is always the same, but I'm going to need this like this left curve down here. And for the other one from 1 to 4, let's look side to side. I still have the same right curve, yeah, exactly, from the head. But now I have this new left curve, which I'm calling L1. So first step is to realize I have to break it into 2 pieces because I have different left and right curves depending on where I'm at. That's the first one. The second part is to figure out what those are. Like, how do you take your curves and and turn them into, well, I'll just do it like this. I have to take my curves. So I've got y equals x plus 2. That's the line on the top. If I convert that into the curve or a function x equals, so solve for x, that'll be y minus 2. I just bring the 2 over. And which curve is that? That's the L1. That's the left curve for the top. That's the line. Here's the tricky part is, how about the other ones? Well, you're like, well, I only have one other function to do, and that's y equals x squared. So where do I get 3 things from? And it comes from, if I solve for x, what do you get? You technically get plus or minus the square root of y. And that's actually 2 functions in one. You can either write this as, you can either do x equals the positive square root, and that is where x and y are all positive. So I'm in the first quadrant. That's the right curve. That's R in my picture. What about the other one? X is negative y squared. Then all of the y's are positive, but the x's have been reversed. So that's the second half of the parabola over here. That's my L2. So now I have my first left curve, my second left curve, and my right curve. So now I can just plug those straight into the formula. So square root of y minus square root 2 square root of y minus negative square root y and square root y minus y minus 2. And in practice, you wouldn't do that. It's just that that's the setup. And if you, whenever you calculate this out to be, it better be the same answer up here as it is when you figure out both of these and add them together.
Thank you, sir.
What else? Anyone else? What other questions? No? Going once? All righty. So get caught up, you know, we can look at this again. Let's see. So homework for today was 7.1. It says homework for Monday is 7.2 and 7.3, but that's just going to be 7.2. We'll push 7.3 back, unless you can figure it out. I mean, if you want to spend the time and not have to worry about doing that from Monday to Tuesday night, you can probably read through and maybe try and figure some of that stuff out, but we'll be revisiting. So 7.2, and then the test will be on Wednesday. So anyway, enjoy the weekend, and I'll see you guys all on Monday.